This is part 6 of the series Congruent Triangles, and we're going to start this session with the converse of the base angles theorem. Remember that the base angles theorem said that if two sides of a triangle were congruent, the angles opposite are congruent. Well, the converse of that says that if two angles of a triangle are congruent, then the sides opposite are congruent. So, without further ado, let's go ahead and prove this theorem to see what's going on under the hood. And so we pull up our proof table, and I've written in the givens, angle A is congruent to angle C. And as we've done several times with many of these proofs, we're going to have to add some information to this picture in order to be able to show that these sides are going to be congruent. So we're going to add an auxiliary line. So we're adding line BD so that it is perpendicular to AC. So let's go ahead and start writing our new information. Draw BD perpendicular to AC. And this is going to be, again, the 2-point postulate. Through any 2 points, there is exactly one line. Now that we know that this is perpendicular, we know that angle ADB is congruent to angle CDB. And this is going to be the right angle congruence theorem. All right angles are congruent. So now that's all we have to say is that BD is congruent to itself. So BD is congruent to BD, and that is the reflexive property of segment congruence. And because this is congruent to itself, I can say that these two triangles are congruent by angle, angle, side. Angle, angle, side. So let's give ourselves a bit of room. So now we say triangle A, B, D is congruent to triangle C, B, D, and that is angle, angle, side congruence theorem. And now because those two triangles are congruent, I know that these two sides must also be congruent. So AB is congruent to BC. And the reason for that, again, is corresponding parts of congruent triangles are congruent. CPCTC. Corresponding parts of congruent triangles are congruent. And that proves the converse of the base angles theorem. So let's go ahead and move on to the next section. Now here we have two theorems whose names alone can be confusing and intimidating. Here we have the corollary to the base angles theorem. Remember, the base angles theorem said if two sides of a triangle are congruent, then the corresponding angles are congruent. Here it says if a triangle is equilateral, then it is equiangular. And we can see that fairly easily. We're not going to do a rigorous proof, but if we use the base angles theorem, we can see here that because this side is congruent to this, we've just proven that this angle would be congruent to this angle. Here we have two more sides that are congruent, and because of that, this angle and this angle must be congruent. So let's try and draw an arc in here. So here we can see this angle is congruent to this, this to this, and clearly all three angles then are congruent. So that's the corollary to the base angles theorem. And then the nastiest name of all, corollary to the converse of the base angles theorem. This is in essence the reverse of this, or the converse of this. And it says if a triangle is equiangular, then it's equilateral. So the converse of the base angles theorem said, if two angles are congruent, then the sides opposite are congruent. So here again, we have two more angles that are congruent. Therefore, these two sides must be congruent. And we can clearly see now that if the triangle is equiangular, it's also equilateral. If it's equilateral, it's equiangular. And those are the two corollaries relating to the base angles theorem. They're fairly straightforward, but it's going to be difficult to memorize the names. And fortunately, we're not going to use the names often, but we will be using the theorems quite a bit. So let's go ahead and look at the hypotenuse leg theorem now, which is the last theorem that relates to congruent triangles. The hypotenuse leg theorem states that if the hypotenuse and leg of one right triangle, hypotenuse and leg, are congruent to the hypotenuse and leg of a second right triangle, then the triangles are congruent. So this looks different than most of the other theorems we've looked at, and so this proof is going to look a little bit different than what we're used to. So I'm going to have to draw a slightly different picture than what we've had in the past to generate this proof. So let's go ahead and bring that up. So here, the diagram, I have back-to-back right triangles. So I have triangle CDB and ADB, and we have the hypotenuse AB congruent to the hypotenuse BC, and angle ADB and CDB are the right angles, and they share side BD. And I finally reached the height of my laziness, and I just went ahead and copied the given in here so I didn't have to write it. So let's go ahead and start working through this proof. So the first thing we should see, due to our temporal proximity to the base angles theorem, is we should see that this is an isosceles triangle because these two sides are congruent. That means that angle A is congruent to angle C. So that should be our first statement. So let's say that angle A is congruent to angle C, and the reason for that is the base, if I could write an E, angles theorem. And so we know that this angle is congruent to this. Now, since we know that these are right angles, we can say that angle ADB is congruent to angle CDB, and that is the right angle congruence theorem, which says all right angles are congruent. And so now we know that these two triangles are congruent by angle, angle, side. Angle, angle, side. So we can say triangle ADB is congruent to triangle CDB by angle, angle, side congruence. So because these legs were congruent, BD is congruent to itself, I was able to put the triangles together, and because the hypotenuse are congruent, then these two triangles are congruent. This is just one version of the proof of the hypotenuse leg theorem. We could have done it a number of ways, but this is just one of the more basic ways to prove the hypotenuse leg theorem. So let's continue on to the next section. This section deals with something called coordinate proof. And what we do with coordinate proofs is we have figures that are generated in a coordinate plane, and we try to find properties and solve problems using the principles that we've come to discover in the coordinate plane. So let's just take a look at an example here. We have this triangle PSR, and we have line OS. And what it's asking us to do is prove that line SO bisects angle PSR. So let's jump in. The way I'm going to work this problem is I'm going to use distance formula to verify that the hypotenuse are congruent. Then I'm going to use that to move forward. I'm thinking if these are congruent, then these angles are going to be congruent. And because this is a right angle, I can use angle side to show these triangles are congruent, and therefore these angles are congruent. So let's see if this works. So SP equals, and we use distance formula. Zero minus negative 3 is 3. 4 minus 0 is 4. And we square, add square root. Difference of the x's squared, difference of the y squared. So that's 9 plus 16 square root, which is square root of 25, which is 5. So we know that this side is 5. Now let's do SR. And we have 0, 4, and this time 3, 0. 0 minus 3 is negative 3. 4 minus 0 is 4. Square, add square root. Again, we have 9 plus 16 square root of 25, which is, again, 5. So yes, in fact, these sides are congruent. So therefore, I can say that this angle is congruent to this angle. So we can say that angle OPS is congruent to angle OR, that's an ORS, by the base angles theorem. And because this is a vertical line and this is a horizontal line, this is a right angle. So I know that these two triangles are congruent by angle, side. So triangle POS is congruent to triangle ROS, and that's because of angle, side congruence. Now I know that angle PSO is congruent to angle RSO because of CPCTC. Corresponding parts of congruent triangles are congruent. So now these two angles are now congruent, and therefore SO bisects angle PSR. Definition of angle bisector. So it's a little bit uglier, it's a little bit less formal, sometimes there's a little bit extra work, but the same properties and principles hold, the same theorems have to be used, but we can do it slightly less formally. So that's just an example of coordinate proof. And that wraps up congruent triangles. I'll see you in the next section.